Yeah, just to make everyone aware, the talk will be recorded, but the recording will be paused when it's time for a Q&A session. So we'll make a start. Today we are joined by Professor Tomáš Polcar, who is a professor of material science and tribology at the University of Southampton. Tomáš pioneered high-temperature tribological properties of protective coatings and solid lubricant during his PhD, and as a postdoctoral researcher, he expanded his research activities to biocompatible materials. He has co-authored over 250 papers and won over 30 scientific projects, including collaborative European projects. Currently, his main research focuses on bottom-up design of materials by combining atomistic simulations and nanoscale experiments for various extreme applications such as space or nuclear fusion and fission. In today's talk, Tomáš will speak about his current research and about his career and what led him to become a tribologist. So, the floor is yours.
So thank you. I hope you can hear me well. Right. So this presentation is quite different from the normal scientific presentation I give because and those you can find in internet if you want to. So what I want to really convince you that there is not easy way to become academic. On the other hand, it can be not really straightforward, but if you really try and you follow this very simple concept, you can achieve whatever you want in your life, whether it is academic career or different, it does not really matter. So I will try to do like my bio in first maybe 25 minutes, showing how I studied PhD, what I learned during the PhD, how I look for postdoc and what I did during my postdoc, and then how I return back to my home university when I really studied as a master, to Prague to start my academic career, and then move to Southampton. So my name is Tomáš Polcar, but everyone in UK knows me as Tomáš Polcar, so you can select whatever you want as my name. I don't mind really. So let's start with content of my talk. So first, I should really say why I start to do PhD, because I think it's quite important. And why tribology? Because it was not really obvious when I was finishing MSc that I will ever go to PhD and never to tribology, to be honest. So then my plan was to, when I finished, to be postdoc in Spain, but I end up in Portugal. So I will try to explain the story behind that, and then what I did actually during my postdoc. Next step in the talk will be about return to my home university in Prague, and then move to Southampton to UK, and it's all connected with building of a scientific group. And then finally, I will show you two case studies, because I should speak a little bit about science. So I will show you two case studies, which hopefully will be somehow connected with all these 3 points above. There was 4 points. Is my startup experience, but I have no time. We can discuss maybe later on in the question about that. And then and as well, a little bit fun, because I do archaeology, I do other stuff, and I think it's nice to show these results. So let's start with my motivation for PhD, and it was very, very different than likely your motivation. So my motivation for PhD was to avoid conscription, because I will provide you during the talk as well some context, because I'm very old. I'm 50 years old now, which maybe doesn't look that old now, but it is. So I will provide you a little bit context. So when I was finishing my master, it was still conscription in Czech Republic, which means to be 1 year, somewhere in the green stuff, going through mud and so on. So not really something I would like to do. The only alternative, and perhaps the only alternative, was to really continue to study. And why it was alternative? Because it was time in 2000 when we really discussed to give up conscription. So I was really hoping they will do it before I finish my master, but they didn't. It was 1 year more. So I said, okay, I will start to do PhD, and then I will give up, and then they will finish conscription. So my motivation was not really to become scientist or to do science. My motivation was to avoid conscription. So yes, but I had to start something, and I like physics. So I graduated as an engineer, something like mixed of thermomechanics and nuclear engineering. But I start my study as investigate plasma properties, because I like physics, I like astrophysics, I like stars. So I was thinking, okay, why not plasma? Then I realized that this is not the plasma I really wanted to study, because this plasma is related during magnetron sputtering, which is really small process you can build in your garage. It's not really astrophysics, but anyway, it started to be really interesting because, like always, when you start to focus on something, you will find the things typically very interesting, and that's, I think, very positive, because it helps you really then to be motivated. So I start to study plasma properties, but then I realized that in my lab we had really very limited properties, very limited equipment to measure any good property. We tried to build something, even I got some funding for that, but I was not very happy. So I told my supervisor, look, that's really pointless to go for that. We cannot really be good in this because we don't have equipment. So I suggested to invest money instead of some plasma physics device to buy high temperature tribometer. And he asked me really why, and I say, look, I was in a conference and they showed a prototype of high temperature tribometer. It means there is no other. It's the first ever available. So we can do something, and we can do tribology. And he asked me, what is the tribology? And I said, well, I don't know, but let's find out. So, and I convinced him that we will buy temperature tribometer. After 2 years of my PhD focus on plasma physics and instabilities in plasma and measuring plasma properties, I will completely change my PhD, and I will do high temperature tribology. And when I was looking for what to measure, the first evidence was really tools, because when you do drilling, of course, your tool gets very hot and it's getting worn. So the idea would be, let's study that. And that's first important thing for you. If you are PhD students, present your ideas to your supervisor. Actually, a good supervisor is really keen to listen to any ideas. If it is silly or not, doesn't matter. Present your ideas, and then you can maybe change your PhD to make better things, or maybe you can realize that your ideas are not so brilliant as it looked in the first time. But anyway, always present your ideas. So what during my talk, I always give you this green stuff, like here, like for small motivation. Okay, so always present your ideas. Okay, so I changed my tribology. I'm tribologist now, and I start to build my lab. And that's what I built, and that's how it looked like, because that's why I'm old. It's about like 2003 now. And what you can see here, this is the tribometer, very expensive thing from Switzerland. We bought like prototype very first. And actually, because of that, we got a lot of visitors of that lab. And funny thing is that most of the visitors were really impressed, but not by this device, by this thing. And why is that? Because in that time, it was LCD monitor. It was one of the first at university at all. So we couldn't imagine, because all monitors were this big square-like TVs. And now it was a very flat LCD monitor. So every visitor was really excited, not by tribology. Whatever I tried to tell them, they always ask me about the parameters of the LCD monitor, you see. So at least you can see how old I am. So, and I am old because next to it, you cannot see, was the communication device we used quite heavily at the university, and was this one. That's actually a phone. If you want to call someone, you use that device, and you expect that someone is close to the next device in the next room. So it was a very different type of PhD, you can imagine, but yet I did it. And I start to measure the samples. But PhD is not only about the science. And after 2.5 years, I say, look, I should really do something else. And I decided to learn Spanish. And how to learn Spanish? So the best way really is to go to either Spain or South America or any other country speaking Spanish. So I arranged study visit in South America. So what I did, I sent email to 3 countries. I think it was Mexico, Peru, and Colombia. I got reply from Colombia and from Peru. Colombia was a little bit difficult because of safety that time. So Venezuela was slightly better. So I decided, okay, let's go to Venezuela. And I went to Venezuela for 5 months to study something about coatings and deposition processes. And it was very interesting, really, because it was 2003. And again, I will put a little bit of history. When I was really packing my things, there was coup d'etat against Chavez, which was president of the Venezuela, and it followed some little bit difficult situation in Venezuela, including 3 months strike. So imagine that you arrive to South America with your backpack, you go to university and you realize university is closed for 3 months. It was really interesting experience. So what I did, I traveled because there was nothing else to do. And I no money as well, so I travel really on very cheap, typically walking or hitchhiking. But it was quite interesting. So I saw almost anything you can imagine in Venezuela. It's absolutely beautiful countries, and I'm really sad about the situation they are in now. But of course, I didn't do much science there because it was simple. But I saw everything, including, I don't know, Salto Angel, the largest waterfall, some very nice animals, as you can see here. And these are really not zoom photos, that you stand 2 meters or you're touching the animals. So it's a really nice experience. But actually, I learned Spanish, and that was the objective. So PhD is not only science. If you think to make a little bit gap, talk to your supervisor, go for 3 months or 5 months to learn something new. Preferably not when there is a strike, but that's what I strongly suggest. But coming back, when I returned, I had no material really to test. So I contacted several companies to provide their coatings, and they did actually. So they were okay. We will give you some material, some coatings, like very resistant coatings to test. And important thing is that we are still in the contact even after 25 years. I see them like every year, few times in fact. Last time they visit me 1 month ago, I think. So, and that's what is important for you. The contacts you build during your PhD, if they are good, they will last forever. And you build your very nice net, which can grow forever. That's fantastic. So please do it. So if you have contact in industry, don't let it die. Try to keep it because it's really beneficial for your future, whatever it is. Either you look for job or you look for collaboration and so on. So it's very, very important. So I will not much discuss results of my PhD because, in fact, I published some papers. They were relatively highly cited, but they were really original not because of scientific content. The science was pure, to be honest, but it was original because of this unique equipment we have. So, and that's very, very important. Sometimes it's better to be first than to be the best in terms of quality or depth of knowledge. Sometimes to be first is very, very important. So don't forget that. And as well, what is the most important when you are a PhD student or postdoc or anyone trying to do some impact, publish and fast, because the world is not waiting and you need to be first and you need to try to publish. A lot of people, they try to polish publications to be really fantastic, and then they miss the train, basically, because if you are the second or third, who cares? So you need to be really the first. So publish and fast. That's really very important message again for me. And then as a PhD student, you go to conference, and I went to conference in South Korea. It was my first international conference. And I was really bold or fool, depends on point of view. And I select oral presentation, and it was accepted, which was surprise to me. And then I started to be a little bit nervous. I'm not that much nervous now when I have a talk, but in that time I was really nervous. And I say, okay, I don't speak really English. I don't know what to say, and there will be full room. And it was really full room. There were like, I don't know, maybe 300 people. And in my very, very bad English, I tried to convey the message. And it didn't work very well, I can imagine. But in fact, there were a lot of interactions, and including one which was Professor Albano Cavaleiro from Portugal. And I just exchanged a little bit of ideas with him and with other people. And this is another message. Even if you think that you are not really excellent, and I wasn't, definitely. And if you think that other people are much better, which very often they are, talk to them. Okay, present your results, talk to people. That's the most important thing, really, for PhD. That's for me if anything, this is the most important. Presentation and talk to people. Okay, so I did. I talked to quite a few people, and then I finished my PhD because, of course, the conscription was gone in that time, but it was too late for me to quit PhD just because of that. So I finished, and I was thinking, okay, what to do next? Either go to industry, which I don't like actually too much, or continue as a researcher, which has some advantages, some disadvantages. So I like to travel, really, personally, and postdoc, it looked like a great way to see the world, because you go to conference, you see the world, and they pay you for that. So I like that. And I spoke Spanish because I learned in Venezuela. So I met aimed Spain, so it was my target, and I got positioned in Portugal. And again, this is quite interesting, I think, to mention here how that happened. In previous slide, I mentioned I was in 2003 in Korea, and I talked to Professor Caballero there. In 2005, I was sending emails to Spain looking for position, and all of a sudden, I got, after 2 years, when we exchanged the email, I got email from Professor Caballero from University of Coimbra saying, okay, we have this position. It was not for me, it was for everyone. There is a very nice postdoc position. If you know someone, could you suggest this position? So I replied, well, I know someone, it's me, I can try. So I applied for the position and I won it. And it was definitely the best step in my life because Coimbra is absolutely a fantastic city. Portugal is a great country. And Albano Caballero, which was my boss there, is absolutely wonderful. So I went to Portugal. But what I want to say here for you when you will look for your next job, don't be too much constrained by your knowledge because my task there was to develop a new fast process producing metal oxides and nitrides, which is nothing to do with tribology. It's more with deposition and some things which I didn't know much about. And I really didn't know what I'm supposed to do, but face challenges. Don't worry, just try. Okay, you can fail, of course, but most of the time you will handle that because you are trained for this. So you are trained to do new stuff, not old stuff. So very often, many students, including PhD students, even postdocs, are too constrained looking for a job. Don't do it. Just try to do face challenges and go outside of the box. Okay, so now what about my postdoc project? So I went to postdoc, and that was my job. It was part of the European project. I was paid from European project, and the idea was really fantastic. So they told me, okay, we can increase deposition rates of oxides and nitrides about 1 order of magnitude if we will pulse reactive gas. I will not go much into detail because it's very complex, but it was absolutely great idea with very, very small drawback that what we realized during the project. It was just impossible. So sometimes you have excellent idea. You can even get, like in this case, it was about 4 million euros just to show that, well, the idea was great. It was worth to try, but it will never ever make any application or anything else basically. So it was basically impossible. But what shall we do with that now? Shall we just say, look, it's impossible, end of story? And definitely no, because we can always get something, even if we realize that something gets really wrong or is not what we expected. So what we did, that we tried to do homogeneous coating, oxide or nitride, but actually we end up with nice multi-layers. So this was like tungsten rich, this is this black part, and it's very thin. You see this is 50 nanometers, so you get like 50 nanometers tungsten. Then we get some kind of, which was oxide, which was gradient oxide, not quite complex. And then again we got multi-layer structure, not really homogeneous coating. So we failed, the project failed. But now I was thinking, look, what is really interesting for me is that this multi-layer structure has very nice colors because we produced the coating and it was green. And we did another one with different conditions. It was yellow, and another one was beautifully blue. And I start to really thinking, is it really interesting to have these coatings? And because they were intrinsic, it means there was no interference. When you change the angle or even the thickness, was really the color of the coating. So I said, okay, maybe we can use that wrong method to produce homogeneous nitrides as a really great method to produce some very specific gradient optical multilayer. And actually, I set up a team of people to help me with that, which was Tomáš Polcar from Sweden, University of Uppsala, and some colleagues elsewhere in Portugal. And we published, I think, very nice paper on nanoscale color control. And you see how far I'm going now for tribology. I did tribology as a PhD. Then I went to Coimbra to work on homogeneous nitrides and oxides. And I end up with multi-layer and I investigate the color just because I noticed that there is a color. And that's, again, my suggestion. So whatever you do, try to look if there is another output, perhaps not directly relevant, but why not? So, and then finally, we end up with some really interesting story to say and to sell. So, and when you have, for example, material to study it. So we prepared oxide and nitride homogeneous coatings by normal processing method, okay? Only to compare with this expected result, which never materialized. But anyway, when I have this material, this oxide and nitrides, and I did tribology during my PhD in Coimbra, very few people did tribology. It was very limited numbers. So I told them, look, why not? We can do tribology of these. And actually, we get 12 papers out of that, which is not bad, I think, as failure, because we failed the project, but in the end, we got a lot of information which were more or less relevant to the project as well. So we proved it's not a good way forward, but we show that it can be used for something else. And I think this is always important to look at it like that. Okay, so it was my postdoc, but what else to do as postdoc? So in fact, if your postdoc is really good, it should be about half of your time. The rest of the time should be kind of free. You can spend either more of this time on your project or do other things. And I did other things. During my PhD, I want to produce molybdenum diselenide coating and like solid lubricant, but the target broke to pieces. So I end up basically with kind of like some small fraction of targets, completely useless. But when I really was in Coimbra, I noticed that they have target, which was placed not above, sputtering down, but it was on the bottom, sputtering up. So my idea was, okay, I can use these pieces, which I will bring from my PhD time. You can see these small squares, more or less here. And I can place them on the target, for example, carbon, and then I can sputter composite material. So if excited like that, I just convince everyone in Coimbra, let's go for it. And because, as I said, Coimbra was great environment, they allow me to do this. So they say, okay, why not? Try it. So I tried. And it was not really new idea to do these coatings. I just was following big guys in the field. They did this composite in different methods. I said, okay, I have different methods to do it. But the idea was the same, produce this coating. And what was the idea behind it? Now coming back to tribology. So the idea was that we will produce kind of like mixture of hard tungsten carbide and soft tungsten disulfide. That was the idea. And then when we will slide it, they will kind of combine together. And what they showed in an extremely well-cited paper was that in dry nitrogen, it was very, very low friction. Friction increase when you change atmosphere to humid air. But then if you go back to dry nitrogen, it will go up. So it can go up and down. They call it chameleon behavior. And then they said that during this is sliding by tungsten disulfide, which is solid lubricant. And in moisture, in presence of moisture, the sliding is based on carbon. And it was really known. They were really known, quite famous group. So I spent a lot of time, about like 1.5 years, to really prove that, just to repeat with a little bit different chemical composition, but prove that this worked. And the result was that it was not really what I achieved. I achieved something like this. You see, I got friction, which was not really changing. Even when I was changing the environment, it was always low. Actually, this one, what you can see, is entirely in humid air. So what I achieved was much lower friction and completely different mechanism. And there were only two options how to explain that. One was that there are two separate mechanisms, or second was that their idea was wrong. So when I had my presentation, it was my first invited lecture. And in the first, there was like 800 people in the room. So again, I was quite young postdoc. And in first row were sitting these big guys, with this. So I described in detail their state of the art and they were nodding. And then I said, okay, and now in the rest of my talk, I will show you that it was actually wrong. And everyone started to listen very carefully, I have to say. And I was right. I was lucky. But what is important to be bold but supportive, So what I did in that time, that I demonstrate that, for example, friction dropped with load, which is typical of these solid lubricants, nothing to do with carbon. Then I really did a lot of tests about the tribal layer. This is worn surface, and I investigated by scanning electron microscopy and EDS, which everyone is doing now, but it was not that common in that time. I used atomic force microscopy to measure nanoscale friction on the surface to show that there is very low friction typical of these solid lubricants. I used Raman spectroscopy, which was almost not used in that time for tribology, and a lot of other stuff, including high resolution transition from microscopy. Know that it was in 2006, 2007. And in that time, for example, I lived in Portugal, but tribology I had to do in Prague because we didn't have tribometer. If I want to do LFM, I had to go to Lisbon because there was no AFM in Coimbra. For Raman spectroscopy, I find one in Karlsruhe in Germany. So I flew to Karlsruhe to do it. And FIB and TEM was done in Switzerland. So I travel all over the world, or Europe in this case, to get the measurement. Now it's much more easy, of course, because we have a lot of equipment. But that's important, try to find collaboration, try to find equipment you need to really show that. And what we observe is this, and that's proof this idea, which I had, that basically we form this very, very thin triple layer. As you can see here, this is very high atomistic resolution here. So you see like rows of atoms, and these are actually 2D materials. It's similar to graphene. In this case is molybdenum diselenide. It's another 2D material. But the important thing is that it was in 2007, and maybe you don't remember that, but the graphene paper appeared in 2004. So it was very, very beginning when people start to speak about these 2D materials for completely different application. And I was able to show them very nicely forming as a tribological process. So it was well advanced, I think, in the time, and I was quite proud of that. And I was right that this mechanism is different than what anyone else before suggested. So be bold. Don't worry about others. If you really can support it with the evidence, as I did, you can put quite strong claims. Okay, and read papers out of your field, because I read a lot about graphene just for curiosity. And immediately when I saw these materials, I said, look, this is 2D material. Actually, there were some pictures in papers before, but people didn't realize that. I think in Tribology, I was one of the first to realize this formation of triple layer. Okay, back to Prague. So I won some project in Portugal, and then I thought, okay, let's stay in Portugal for life. We really like that. I had my first kid there, but then from personal reason, I had to move back to Prague, and I decided to move back to my Czech Technical University, but change completely faculty and department, and I went to Department of Control Engineering. And this department has absolutely nothing to do with tribology. They do robots, automation, these things. But it was one of the best departments at the university. And that's what I, again, suggest you, okay? Always select the best place, even if it is not necessarily exactly. If you can go to Department of Mechanical Engineering or group of Tribology, which is bad, or you can go to absolutely excellent AI department, go to AI and do Tribology there, okay? So select the best place, not necessarily the one which is fitting the most your CV or that. That's, I think, very important message I have for you. And I did, and it was very good because they allow me to do tribology there. They just say, okay, we will try to support you, but show us that you are able to build your group. And I did. So I started to build my group. And then after a couple of years, I really got email. I got email offering position in NCATS, which is National Center for Advanced Tribology in Southampton. And I thought, why not to go to UK? So I applied, I got the position, and again, select the best place, because in that time, and even today, I'm thinking this is a very good place to do tribology in the world. So why not Southampton? So I was selected, and I started my job as a lecturer here in Southampton in 2011. So when I started, I really was lucky because several things happened in that moment. And you remember that I did this unsuccessful oxide multilayers. That was this European project I started to do as my postdoc. But based on these papers showing that it cannot work, I was invited by a team which I never heard about to join European proposal, and we actually got it. So I got my funding, quite substantive. The project was aimed at the interface design resistance to radiation damage. This is nuclear science or nuclear material science, nothing to do with tribology. And I was invited because we failed in another European project. So you see that sometimes what you think is failure is perhaps not that big failure in the end. So what I did that I just said, okay, why not? Why not to change subject suddenly and do something else? And the same happened with my first PhD student here in Southampton. It was Mauro Callisti, it's absolutely brilliant guy. And he was interested in shape memory alloys. And I just knew something that they exist, but really nothing more. So I said, okay, look, convince me. You have first 3 months in your PhD to convince me that we can do anything interesting on shape memory alloys. And he did, actually. He showed me. And so we tried that. And on top of that, because he was an excellent student, I involved him with this interface project, which I mentioned just there. And as a result, we published together 27 papers, which I think is pretty good achievement, and most of them in really top journals. And we had very good time together as well. When we went to conference or elsewhere, you see that we are really taking a break somewhere in Aspen in Colorado, or extremely good dinner in Azores in Portugal, in islands in the middle of Atlantic Ocean. So it was really great. So, and we are in touch and in contact till today. And this is another important thing. Try to build your net of people, because if they are good and you have good collaboration, you can really collaborate with them together. By the way, last paper with Mauro we published was last year. You see that more than 10 years after his PhD. So I think it's really great. So I started in Southampton. I built my career, built my group, but I was now deciding what to do experiment or theory. And that's a big question, of course, because typically you can do one or another. It's very, very difficult to combine both. And I'm experimentalist. I don't know much about theory, but I understood the importance of theoretical simulation. So I looked for collaborators, and finally I start to hire people in my team to do simulations. And these are two examples, and now more scientific, more tribological, which I will show here. So first one is related to the solid lubrication. You already seen something before. So based on that, I just say experimentally, I observe this formation of triple layer, but we need simulation to understand it and to design materials. And I wrote a material project, which was European project, about 3.5 million euro. And I was lucky enough to get one. It supported 14 PhD students. And who was the partner there? So I was coordinator from Southampton. Another partner was University of Coimbra. This is where I did my postdoc. Then Czech Technical University in Prague. This is where I studied, and then I got my first lectureship. Then the Burgos were the guy who invited me to that project related to nuclear damage. So I invite them for the project doing simulations of triple layer. See, so and you see that how things really can combine together. So something you do, you may forget, and after 2 years, 3 years, it may appear. And if you are really active and bright enough, you can take the opportunity and use it. So you see, I built my team, I built my connections, and then I can use that. And that's what you should really try always to do. So I have my project now. I have a lot of money. I got 4 million or 3.5 million euro from this, and I got 4 million euro from other projects. I have a lot of money really to do. So we try to do something. And basically, I select like two major tasks for me. One is sliding of these 2D materials to understand more. And then this formation of triple layers. So this is like very nanoscale, and this is a little bit macro scale sliding. And I will show you now in next 5 minutes something what hopefully we achieved, which was really nice. So first, we need to figure out how to measure this friction of 2D materials, because it's not so easy as you can imagine, because this is something which is like one layer of atom like graphene, or three layers of atom like molybdenum disulfide. How can we really measure it? So we developed completely new method. So when you put the flake, like this one, very small flake of 2D material, on something like very large flake, what we said, we can use atomic form microscope in lateral form mode to push it. So we will basically push this flake. And when we push the flake, we can measure friction. Because friction, we will measure really directly. There is no other effect than just the friction. So that was the idea, and actually it works. And it works like that. You slide your AFM tip over the surface from left to right, and it's this low friction here. And when we will hit the flake, of course, you need to increase now the force, which is this difference, to start to move the flake. And this difference is exactly friction force induced by sliding of this small flake. So we were able, as a first in the world, I think, to measure genuine 2D to 2D friction with any other influence. And then when you want to increase the load, you would say, okay, but there is no load, there is just adhesion. But we said, okay, we can do another thing. We can touch basically the surface here, touch the flake somewhere in the middle, and then drag it. And because friction between the tip and flake is typically higher than between flake and the substrate, which is another flake but bigger, your tip will stick on the surface, and you can really move it back and forth. And again, you measure the force. So we developed a new technique. Here in movie, you see that we were able to move the flake, so it worked perfectly. And now we could measure friction. So when we calculate the friction, we got value which was 10 to minus 6. It's 1 millionth. Okay, so it's one of the lowest friction ever measured for solids. And in fact, if you really go a little bit more in details, very likely the friction can be even lower than that. At least our simulations show that. And in the paper, what we did a lot of work in the paper, but we combine this molecular dynamics in this case, and a little bit of initial simulation to confirm the experiments. And that's the importance of combining experimental work and theoretical work, because in experiment, we show this very low friction, but in theory, we explain why we get that. And that was really cool. So it was published in quite decent journal, but the most important in this journal is this. And Victor and Andrea, these were my two PhD students. So which I shared, of course, with other researchers, and that's the major achievement. In fact, it's not really that we published papers, but that it was really that our students really contributed in very, very important way. In both cases, they did simulations to that paper. So that's what I'm really proud of. Okay, so this is the paper, and then the idea was, okay, we now know how to slide these extremely small flakes, but what about bearing or something bigger? So the idea is that if we take the ball and we somehow cover it with 2D materials, and we will slide it on other 2D materials, maybe we will have again friction to minus 6, and we will achieve frictionless, and we will be extremely rich because everyone will use our material. So we try to cover the ball. But the problem, if you cover the ball, you see that you have these wrinkles because you try to really cover 2D material or 3D material, which is ball, by 2D material. So it cannot really fit very well. So you have some wrinkles, some problems here. And in fact, because of that, we realized that it will not work because these wrinkles, it's very easy to be broken. So we cannot really, we just destroy them. There was no way how to convince this system to reduce friction to 0, because we almost immediately destroy one or another 2D material. But again, the story is not about to try and to fail. The story is to get maximum from the failure. So it didn't work, and yet we wrote a paper and it was published in Applied Material Science where we explain why it doesn't work. So we said, look, we get these wrinkles get broken very quickly, and we develop kind of model. You see the ball, which is tip, which is going. I don't know why the movie is not continuing forever, but you see that we have a model which show how it breaks basically this kind of like wrinkle. And because we cannot avoid the wrinkle, we cannot really make this material working. So it's so you see that even if you fail, you can get something. And then I went back and we did some simulation. Again, I will show it very briefly without much explanation what is possible now, just to demonstrate. So we have some experiment. This is the friction coefficient measured. Then we can see that there is some triple layer formed. And then we can do some simulation, try to predict that. And you will see this in this video. So you see that we have simulation. It shows here that we form this very nicely aligned tribal layer. And even when we change some parameters, we still form it here or even there. You see it start to form. So basically now we have the model which show us how to make basically the sliding very, very effective but by simulation. So not today, but maybe in 3-5 years, we will be able to use this atomistic simulation to really predict the properties and open this bottom-up design of new solid lubricant and other, of course, materials. It would be great. Okay, so, but it took me 15 years to get there. I did many other things, but 15 years to get there. So it takes some time. Okay, another thing to show in tribology, how you can really connect other areas with tribology. So I mentioned that I was invited to this European project for these interfaces, resistance to neutron damage, basically, nuclear science. So we produce these multilayers. This is, you can see, this is very, very thin multilayer. This is multilayered coating with something like 3 nanometers of zirconium, 3 nanometers of niobium. Very, very thin multilayer. Because you are interested in interfaces. I will not mention anything about these neutron damage or helium bubbles growing there, but I will show you tribology, because we had everything, and when we study everything, I said, why not to study tribology as well? No one ever did that, and we will use molecular dynamics for that. So again, we did some simulations. We use the tip, there is this multilayer, as you can see, and we just slide the tip. And then something we cannot do in experiment, we can in simulation make it perpendicular. I don't know how to produce it, but in model you can do anything, and we try to see really how it works. So that's what the result of simulation is and what is possible now. So you can see all the damage, you can see the effect of interfaces, how the dislocation, which is the green lines, this is dislocation net, and you see how can they propagate or be stopped by interfaces. And you can really understand the processes and use them in simulation. You can now simulate coefficient of friction. It was not possible 10 years ago. And you can even see what happened in, if you want real time, when you have your tip moving and scratching the surface, you see below the surface how the dislocation evolve and how they penetrate through this interface. You see they get stop interface, some of them penetrate, and then when ball will go through to zirconium, you will have completely different dislocations because it's different material. But now we can do all that, and that's really fantastic. And again, we published in excellent journal, got a lot of citations, and it's just sideway of the project which normally looks for nuclear engineering. So try to combine the things. And in last 3 minutes of my talk, I will just highlight one more thing. So my strategy is to know nothing about everything. Actually, most of researchers, which I know, they know everything about nothing. So they are really expert, but they are very, very narrow field. And I think it's not good. I think you should really read and learn more and sacrifice a little bit that you don't know everything about your area. But tribology is really everywhere and can lead you anywhere. And in my case, for example, if I find I like Navy, and what happened that thanks to tribology, I went with my colleague Julian Wharton from Southampton in a frame of one project to investigate how slippery is the flight deck of Queen Elizabeth aircraft carrier, which is actually not very common. You go to active warship during it was in Portsmouth. So you can do anything with tribology, really, including archaeology. I like history, so I talked to archaeological department and I told them, what can we do in archaeology? Can we do something together? And yes, so we had a project when we investigate bronze axis. It was Miriam Anders, my PhD student, and then she prepared, I don't know if it is visible, she prepared the axis using the same method as they used 3,000 or actually, 3,000 years ago. And then we test them intensively either in the field or in the lab using high-speed cameras. This is actually me trying to hit some wooden block and use high-speed camera to see the damage. So what we investigate was the wear and scratches on and polishing effect of the bronze axis, and this is some results of here. And then we compare our results with those found in museum, and we publish very good papers as well about that. So tribology is really everything, and you can really talk to people doing history, doing archaeology, doing anything. So it's a great topic to be in. Okay, so what is your next step? And actually, my last suggestion here is consider startup company. Unfortunately, in the UK, for whatever reason, most of the students, they do not consider make startup or even to be employed in one. everyone wants to be employed in large companies. They are not bad, of course, but really, I strongly suggest do startups. I launched 2 startups and 1 spin-off. One failed, didn't work at all. After 2 years, I sold my part and forget. But 2 are doing quite well, and they employ more people doing really high-level engineering. So please consider this as option. And the way is sometimes difficult. Sometimes you try to cross, and there is a gap. You have to jump. But if you decided to jump, typically you end up on the second bank, and you will learn something. So that's all from my side. Thank you for your time, and I hope I will get some 10 minutes for questions.